closely related problem to what we were just talking about is the following. So let's say we have a plane out here and we've got some other random point and we want to know how close is that point to the plane? How much of a distance does it have to travel to get not just to some random spot, but to get to the closest possible spot on the plane that there is. So that's what I'd like to cover next. There's a very clean formulation, again, using the dot product. If we know the data in one way, then there's a particular formula for it. Namely, it looks almost exactly like the formula we had for the plane on top. We take the normal vector dotted with our vector q minus our point p, but then instead of setting that equal to 0 to find the equation for the plane, what we do is we divide by the length of the normal vector. And the point of this is that it uses some vector geometry. What we want to know is this distance here that goes from point Q down to the plane. In order for that distance to be as short as possible, that line should make a right angle to the plane. And so, since I know that this angle here, theta, is the same as the angle made by the vectors n and the vector from P to Q, I can say that this height here should be the length of the vector from P to Q times the cosine of the angle between them, and so that's this part here. In order to get the whole thing, I should divide by the length of the normal vector. There's an absolute value on top. The absolute value is just thrown into there because we might get a negative number, and we get positive or negative depending on whether our point Q is on the same side of the plane as the normal vector points or whether the point Q is on the opposite side of the plane. Now, if we don't have that data, if we don't have a point and a normal vector, but we instead have the equation for a plane that looks like that, there's a shorthand form that doesn't require us to do any adjustments. What we do is we basically say, if we want to know the distance from a point x, y, z to the plane, we just plug it into the equation for the plane and then divide by the length of the normal vector, ABC. So that makes it very, very clean and doesn't require us to go through all of this vector geometry. So this is a handy formula to remember if you're trying to solve for these kinds of things because it skips some intermediate steps.